I've decided to put a video out on band theory so that Year 9 students can explain what transparency is. But it seems that it sort of like interacts with a lot of other syllabuses around the place. And so I'll just keep going. And so if you're watching this and you're in Year 9, just keep watching because in Year 10, 11, and 12, it might help you understand a few other things as well. Okay, so first experimental evidence. This comes from the Wise Glass Transparent. And I'm doing a little bit of a focus on glass because we use glass a lot, and chemistry, physics, biology wouldn't progress without glass. They say that's the greatest discovery because you got telescopes, microscopes, and chemistry's got glassware, which was all that sort of stuff's needed to progress the subjects. And so he puts in this here, 574, and then he lowers the energy of the photons. And when he lowers the energy of it, it goes through the material. And so the lower energy, which is at less than 569 nanometers of light, which is in the reddish area, allows light through. So that's the experimental evidence, and this is the theory behind it. So the theory is band theory. It's for solids, and it's to do with the interaction with the electron. So this probably helps if you're searching for it to not look up like musical bands or Big Bang theory. Solid state electrical band theory. So I do as much as I can, and then I have to go to AI for some things. All right. So it's sort of not easy information to find. Okay, so the idea is you've got these electron shells, and the electrons need energy to move up into a shell. And so the valence bands, the valence shells are what you learn when you did the 2888 shells, concentric circles. When you get to year 11 chem, you'll do a little bit more detail about what those shells actually are. They're three-dimensional things. And then if there's gaps, when they move up into a higher shell, that's called conduction because the electrons are free to move. Remember, we're talking about solids here, so we won't talk about other things, liquids and gases, etc. And so what you've got here is for something like a metal, you've got it. It's very easy because there are gaps in the same shell. So the conduction band, which is here, it's very easy there's no extra energy needed, so it moves the electrons very easily. And if there's a gap there, then it requires some energy to be input for the electron to jump up into that another shell where it can move. Okay, so that's called the band gap. The purple ones here are the valence bands. These are the inner shells here, and you don't want a gap between this free area and this area if you want it to conduct. Okay, so just going on from there, so you need to take from there, just appreciate valence bands, conduction bands, and band gap. It's the only thing we're really looking at. Now light has wavelengths. These are small wavelengths, 390, so that has a lot of energy per second, and these ones are larger, so there's less waves per second. So that's the red is the less energy, and the purple is the high energy, so they're opposite. Okay, so low energy is red with a large wavelength, high energy is purple with a small wavelength, and there's all the bits in between. And an electron volt is just a unit we're using to say how much their energy there is. Okay, so if you're going to excite if you have a high energy over here, small wavelength, then you're potentially going to have more energy to raise an electron if it's got a large gap. And the large gap will be a larger electron volt gap. And for the light region, that's calculated. The year, I think we're talking IB now. High level IB, year 11, will actually be doing the calculations. I'm not sure about the physicists, sorry. Okay, so the other thing you need to know is the color wheel. So as far as your eyes are concerned, if a substance looks blue, it's probably because it's absorbing a lot of energy in the orange area, or if it looks orange, it's absorbing energy in the blue area. And so that we use a color wheel to sort of determine, well, if you're seeing one color, or if you've got one color, this is the wavelength that's getting absorbed most by the material. And that helps us determine which colors to use for a machine or what the energy gap might be. Okay. And so moving on to transparency. So this is, if you get nothing else from this and you're in year 9, it's transparent because the photons don't have enough energy to be absorbed by the electrons. And so they go through. And that's based on different material. Okay, so if there are large band gaps in the photons of light do not have enough energy to excite the electrons to the conduction band, photons are hence not absorbed and go through the material, and the material is transparent. That's what you need to get. Okay, but really the rest helps you understand a lot more than that. Okay, so the band gap in particular is this. So if the band gap is in between this, you may end up seeing these sort of colors. It's different for every other material. I'll go into that in a little bit later. I've done this one up here with the color wheel, so let's go up here. So this has got quite a large band gap, and so it takes quite a lot of energy. So it's absorbing the blues the most, and so what you end up seeing is the yellow. Okay, now some materials, because they'll absorb all the colors, will turn black. And if they don't absorb anything, sometimes they can appear white. Okay, so there's a little bit of variation when you're in the color spectrum region. But generally, if it's higher than 3, it's transparent, and lower than 1.8 or around that value, it is opaque. All right. Moving on, we'll just focus on glass in particular. It's just easy to get AI for this. So the photons, so what's happening in glass is the photons, so this is an electromagnetic wave, and if it's a small wavelength that's got more energy, what it's not doing is it's not having enough energy to be absorbed and increase the electron to the next shell. So all it's doing is it's still here, but it's vibrating, and then that is then moving that energy along throughout the material. So that is why the wave front slows. Hopefully you're doing Huygens wave theory to explain refraction. And so because it slows, that is refraction. And so the wave slows down and bends. Okay, I'll leave that for in detail talking about refraction, okay? But that is what's happening. It's just vibrating and then moving that vibration on, okay? And so it doesn't get absorbed, and it gives sort of this elastic transfer of energy all the way through, okay? And so what you see is a clear image. It's not just clear, it's also a clear image as well. Okay, so it's actually the low energy electromagnetic radiation go through, one way to think of it, or the other way to think of it is it takes too much energy for light to be able to absorb, to move that electron up to another shell, so the light just goes through instead. Okay, just to, you're probably wondering, well, why is it not always transparent? There might be some large gaps. I'll just give you a very easy one. Calcium carbonate is usually given to you in a bottle with white powder to react with stuff. If you get it in a crystal, it's actually quite clear. It has double refraction too, which is interesting. You get it much clearer than this, by the way. You can see there's fractures and stuff in here. And there's just the second and last AI slide. This is probably the most important one. This one here, if it's smooth or not. Giving you reasons why it's got a high EV gap, but still the light's not getting through. The light still manages to get absorbed into it, even though it shouldn't, because it takes too much energy to interact with that and absorb that electron to a higher shell. So now moving to allotropes. For year 11 chem, we'll probably do a better job with bonding to explain why it conducts electricity or not. That's what you're meant to do. Just be aware that this one has no band gap and this one has a high band gap, so it doesn't conduct electricity. But you're not going to use that to explain it. You're going to use the types of bonding. And so there's free electrons in between the sheets, etc. So this one I just wanted to explain why that one's transparent and that one's opaque, and that's to do with the band gap. Okay, so this one has no band gap, so the photons can interact with the electrons and absorb to higher shells. And this one has a large band gap, so the light passes through, not held. So that's very similar to glass, right? So that's the key for what is transparent and what's not transparent. And lastly, for year 9s, why is something reflective? Notice this is very flat and polished. so it's not diffusing out in different directions. And so that because there's no band gap or even an overlap of the gaps, there's a high number of electrons in the conductive bands, and so there's a high level of interaction with the electrons, so the photons bounce straight out, and that's what's special about what makes metals so shiny. Now moving on to conductivity, this one I'll just be very quick. So as you know, that is to tell whether it's transparent or not. Anywhere in between this light sort of level is called a semiconductor. So that's a very small band gap, and on the left hand side there's no band gap or there's an overlap, so it's a metal, and on the right hand side if it's greater than about 3 it's considered as an insulator. Now this one's more for 10 advanced, which is really 11, 12 physics, and I'm not going to talk about the depletion layer. So this is all about the depletion layer, or to create holes. I haven't even said depletion layer, which is fine, but just to incorporate a little bit of extra stuff into your understanding of semiconductors and doping. So if you add extra electrons or less electrons to the semiconductor, you're going to actually help it to be more conductive, and we'll talk about depletion layers later when you talk about actual semiconductors. So here, the extra electron, so you've put an N-type, so you put a phosphorus, so it's different from silicon in that there's an extra electron available. All right, now this electron will be an excess electron, not held as tightly to the nucleus, and so that means the conduction band will be much easier to reach, so the band gap is decreased that way. This one here, you've created a hole, and that makes electrons much easier to escape from, and so the valence band difference is not so great, and so it's easier to pull electrons out of the valence shell, so the energy level's a little bit higher here, so that's why that band gap is decreased and it conducts better. And I'll leave the in-depth diodes, transistor stuff for that as a particular lesson, but this is how it relates to band gap.